Something is at play in our cognizance of the universe. Cosmology is by all accounts heading for a stalemate on one of its most fundamental questions: how quick is the universe developing? For more than a decade, two kinds of assessments have been in struggle. View of the current universe conventionally tracks the pace of improvement, called the Hubble steady, to be around 9% speedier than assumptions. In view of early universe data, scientists trusted that the James Webb, the most high-level telescope at any point built, would help with settling the request. However, it has up to this point neglected to arise. Rather, the Transcendent Observatory has cemented the mistake with incredibly careful new insights that make moves to upset the standard model of cosmology. The new actual science, expected to change or attempt to replace the 40-year-old speculation, is at present a subject of discussion. A shocking and interesting credibility is that there's something we make an effort not to fathom about the universe. Join us as we plunge deep into new, ultra-depth pictures from James Webb. As of late confirmed, there is something genuinely amiss with how we could decipher the universe. Our universe began with a bang, the enormous detonation. Energy, mass, and space streamed into presence all inside a short-lived second. Then the young universe was formed, an expanding roiling plasma load of matter and antimatter particles that jumped into reality just to obliterate each other upon contact. Just let potentially run wild, the matter and antimatter inside this plasma should have consumed each other totally. However, researchers believe that some obscure disproportion enabled more matter than antimatter to be produced, saving the universe from quick collapse. Gravity compacted the plasma, pockets squeezing and warming the matter so that sound waves, traveling just over around half of the speed of light, called baryon acoustic oscillations, undulated across their surface. Meanwhile, the high energy density of the early universe's compacted contents expanded spacetime, pulling a little piece of this mass securely from the burn. As the universe expanded like an air bubble, the standard story goes, typical matter, which interacts with light, coagulated around bunches of imperceptible dark matter to make the primary universes. Associated together by a huge cosmic web, at first as the universe's substance spread out, its energy density and subsequently its extension rate decreased. However, then around 5 billion years back, systems started to withdraw once more at a consistently quicker rate. The reason was another imperceptible and baffling element known as dark energy. The least complex and generally well-known clarification for dark energy is that it is a cosmological steady, an inflationary energy that is something very similar all over and at each second, woven into the growing texture of spacetime. Einstein named it lambda in his hypothesis of general relativity. As our universe developed, its general matter thickness dropped while the dark energy thickness continued as before, progressively making the last the significant supporter of its generally extension. Added together, the energy densities of standard matter, dark energy, and energy from light put forward the upper speed line of the universe's expansion. They are likewise key fixings in the lambda cold dull matter or lambda CDM model of cosmology, which guides the advancement of the universe and predicts its end with the matter in the then spread that far experiences a power demise, called the Big Freeze. Many of the model's predictions have been demonstrated to be exceptionally exact, but here's where the issues start. In spite of a lot looking, space experts don't have any idea what dark matter or dark energy are. As Ofer Lahav, a teacher of cosmology at College London who is engaged with cosmic system investigations of dark energy, said, the vast majority concur that the universe's ongoing structure is 5% customary atomic matter, 25% cold dark matter, and 70% dark energy. The humiliating truth is we don't comprehend the last two of them. But an even more prominent danger to the lambda CDM model has appeared. Depending on what technique astrophysicists utilize, the universe seems by all accounts to be expanding at various rates, an inconsistency known as the Hubble strain. Techniques that peer into the early universe show it expanding altogether quicker than lambda CDM predicts. Those techniques have been investigated and affirmed by countless perceptions, so is Nobel Prize-winning astrophysicist Adam Rees, who led the group that made the new James Webb estimation, said, the main explanation that I can comprehend as of now for the contrast that we have makes between them is perhaps absent something in estimating the universe's expansion. It takes a smidgen in excess of a radar weapon. The primary strategy to gauge this expansion rate takes a gander at the purported enormous microwave foundation or CMB, a leftover of the universe's first light produced only 380,000 years after the enormous detonation. The engraving ought to be apparent across the whole sky, and it was wanted to see as a Hubble study with under 1% vulnerability by the European Space Agency's Planck satellite between 2009 and 2013. In this cosmological picture, the universe is generally speaking uniform but more blazing and colder patches where matter is more or on the other hand less thick reveal where bar on acoustic movements made it pack as the universe detonated outward. This soap bubble structure ventured into the infinite web, an organization of tangled strands along whose intersections universes would be brought into the world. By concentrating on these expands with the Planck satellite, cosmologists gathered the measures of standard matter and dark matter and an incentive for the cosmological consistent or dark energy. Stopping these into the standard model spat out a Hubble steady of around 67 km per second per megaparsec. We ought to stop on this number briefly. If a world is a distance of 1 megaparsec away from us, then at that point, that would mean it will retreat from us and is from it at 67 km per second. At 20 megaparsecs, this downturn develops to 1,340 km per second and continues to develop emphatically from that point. Assuming a universe is any farther than 4,175 megaparsecs away, it will retreat from us quicker than the speed of light. A second strategy to find this expansion rate utilizes throbbing stars called cepheids, passing stars with a helium gas outer layer that extends and contracts as they absorb and transmit the star's radiation, making them periodically flash like far-off signal lights. In 1912, space expert Henrietta Swan Leavitt discovered that the brighter a cepheid variable was, the more slow it would flash, enabling cosmologists to gauge a star's outright brilliance and along these lines measure its distance. It was a breakthrough revelation that transformed cepheids into plentiful standard candles to gauge the universe's enormous scale. By hanging perceptions of cepheids together, cosmologists can assemble grandiose distance stepping stools, with each rung taking them a step once again into the past. It's one of the most dependable implies that space experts have today for estimating distances. To assemble a distant stepping stool, space experts develop the principal rung by picking nearby cepheids and cross-checking their distance in view of throbbing light to that found by math. The following rungs are added utilizing cepheid readings alone. Then stargazers take a gander at the distances of the stars and supernovae on each bar and inspect the amount of their light possesses been red moved to longer, redder frequencies as the universe grows. This gives an exact estimation of the Hubble steady. In 2019, the technique was utilized by Rees and his associates, who prepared the Hubble Space Telescope on one of the smooth way's nearest neighbors, the enormous Magellanic Cloud. Their outcome was a gigantically high development rate of 74 km per second per megaparsec, contrasted with the Planck estimation. However, Hubble without key accuracy for the swarmed areas of the room the group was zeroing in on, causing some far-off cepheids to obscure into nearby stars. Conflicting cosmologists had some room left to contend that the outcome, however, shocking, may have come from an estimation blunder. So, at the point when James Webb sent off in December 2021, it was ready to either determine the disparity or cement it. Webb's reflect is simply over 2 times the size of Hubble's, which is simply 2.4 meters wide. Not just could James Webb recognize objects 10 times fainter than Hubble can, however, it is additionally substantially more delicate in the infrared range, enabling it to find in a more extensive scope of frequencies. By contrasting stars measured by James Webb in the system NGC 4258 with type IIA cosmic explosions, another standard flame since they generally burst at a similar outright glow in far-off worlds, Rees and his associates shown up at a practically indistinguishable outcome, 73 km per second per megaparsec. Different estimations, including one made by Friedman with the Hubble Space Telescope on the quick lighting up of the most splendid tip of the branch red Goliath stars, and one more with light curved by the gravity of gigantic universes, got back with explicit outcomes of 69.6 and 66.6 km per second per megaparsec. A separate outcome utilizing the twisting of light likewise gave a worth of 73 km per second per megaparsec. Cosmologists were left reeling. As indicated by Ryan Key, a cosmologist at the College of California, Merced, who has been working to sort out the Hubble strain, the CMB temperature is estimated at the degree of 1% precision, and the Cepheid distance stepping stool assessment is drawing near 1%, so a distinction of 7 km per second, although it's not huge, is very probably not going to be an irregular chance. There is something unmistakable to sort out. The new result leaves the response totally open, separating cosmologists into camps seeking after immeasurably various arrangements. Following the Hubble Space Telescope result, an official endeavor to determine the issue at a 2019 meeting at the CFA Institute for Theoretical Physics in California just caused more dissatisfaction. As the late Vera Rubin, who found proof for dark matter, said, at that time, nobody wanted to surrender their toy. All individuals included accepted so emphatically in their own results and thus unequivocally in the manner that their observations and their estimations were done accurately. It just left individuals needing to sort out how to sort this out. In February 2023, with James Webb and another independent Hubble Distance Stepping Stool result affirming the Hubble strain, cosmologists are left with 3 likely clarifications: estimation blunders, new physics, or some mix of the two. A large portion of the information upholds new physics. The least complex and most well-known hypothesis is that dark energy acts distinctively today than it did in the early universe. If dark energy was strong at one time and then disappeared, it would make the universe look smaller when we think back to the early universe, making the expansion rate appear quicker. There are different clarifications, for example, the possibility that there are 2 kinds of dark energy or that dark matter interacts with light, but these explanations present inconveniences that cosmologists are wary of. Without further information, dark energy and dark matter aren't the only secrets James Webb is serving to settle. When it sent off, it was entrusted with looking further back in time than any telescope before it. James Webb's progressive new imaging technology enabled it to see galaxies formed just 300 million years after the Big Bang. However, while examining the universe's beginning, cosmologists saw that as these early galaxies are substantially more massive and advanced than the Standard Model predicts. Early galaxies should have been full of young, hot stars forming at a very fast rate, but James Webb showed many of them were spilling over with heavy elements from earlier ages of stars and actively growing bulging places of supermassive black holes. Let's break down this fascinating subject further: the basics of cosmology, the Big Bang, and early universe. The universe started around 13.8 billion years ago in a hot, dense state. Not long after the Big Bang, it expanded quickly, leading to the universe we observe today. Measuring the growth rate. Early universe measurements using the cosmic microwave background (CMB) provide one method for measuring the universe's growth rate. Current universe measurements observing pulsating stars, Cepheid variables, and type Ia supernovae offer another method, yielding a higher growth rate than expected by early universe measurements, the Hubble strain. This disparity among early and current universe measurements suggests likely errors or the need for new physics. James Webb Space Telescope capabilities. With unmatched precision and sensitivity, James Webb confirms the higher growth rate seen with current universe measurements, confirming inconsistencies. James Webb's findings confirm existing inconsistencies and prompt a reassessment of cosmological models for potential adaptation, measurement errors, new physics, or some combination of the two. Early universe and plate revelations. Surprising attributes. James Webb's observations reveal early galaxies with remarkable properties, challenging existing models of galaxy formation.